Hi, I'm Cole.
And I'm Grace. Welcome to the Deep Dive.
Welcome, everyone, to the Deep Dive. Today we're embarking on an intellectual adventure, plunging into the mind of a true titan in artificial intelligence. Imagine an AI pioneer, one of the three acknowledged godfathers of deep learning, looking at all the incredible advancements we see today, the chatbots that write poetry, the image generators that create impossible art, the systems that diagnose diseases, and stating, quite unequivocally, that despite all this hype, current AI models are still, and I quote, dumber than a cat.
It's an incredibly provocative statement, isn't it? And it comes from Yann LeCun, a name that's not just synonymous with foundational breakthroughs in AI, but also with a fiercely independent and often contrarian vision for its future.
Right.
His perspective isn't merely a casual remark. It's a deeply informed critique from someone who, alongside Geoffrey Hinton and Yoshua Bengio, received the prestigious Turing Award back in 2018 for their work that fundamentally transformed the entire field of deep learning.
That's why his voice resonates so powerfully. His insights don't just shape the formidable AI strategy at Meta, where he serves as chief AI scientist. But they genuinely influence the entire global conversation about the ultimate potential and, maybe more surprisingly, the limitations of intelligent machines. So what does it truly mean when someone of his stature makes such a bold and, well, seemingly dismissive statement about the very technology he helped birth?
That's precisely the central question we're here to unpack for you, our listener. Our mission today is to take you on a journey through Yann LeCun's remarkable career. We'll explore his groundbreaking contributions, particularly the revolutionary convolutional neural networks, which literally changed how machines see.
Yeah, the scene part is key.
Absolutely. Then we'll dive deep into his current, often controversial, views on AI's trajectory and examine what his compelling vision means for understanding AI's real potential, its current stumbling blocks, and the truly fascinating challenges that lie ahead on the path to, well, genuine intelligence.
Okay, let's start at the beginning then. Yann LeCun's path to becoming one of AI's most influential figures began with a pretty rigorous academic foundation. He embarked on his scientific journey, studying at the École supérieure d'ingénieurs en électrotechnique et électronique. Quite a mouthful.
Ah, yes!
And then completed his PhD in computer science at University Pierre et Marie Curie in 1987. This early academic rigor wasn't just about accumulating knowledge, right? It was about laying the groundwork for a revolutionary approach that would fundamentally redefine how machines, well, perceive the world, how they turn raw data into meaningful understanding.
And this foundation led him to a truly pivotal period in his career, his formative years at AT&T Bell Laboratories, starting in 1989. This wasn't just any research institution. It was a real hotbed of innovation back then.
Bell Labs, yeah.
Yeah, totally. And it was here that LeCun spearheaded the development of what we now know as convolutional neural networks, or CNNs. What's truly remarkable is the context. In 1993, at the relatively young age of 32, LeCun demonstrated the world's first practical CNN for handwritten digit recognition. Imagine, at that age, laying down a cornerstone for an entire field that would just explode decades later.
It's incredible to think about the historical context here. This was a period widely referred to as an AI winter, right? A time of deep skepticism and significantly reduced funding for AI research.
Exactly. The initial hype from earlier AI approaches had kind of faded, leaving a chill in the air.
Yet in this unfashionable climate, LeCun was quietly, persistently building something profoundly impactful. It makes you wonder about the mindset required, to continue groundbreaking work when the world isn't really paying attention.
Takes real conviction.
There was that quote, someone looking back said, "I'll never understand why this didn't blow up like it should have. AI winter my backside." This work, despite its profound implications, was perhaps underappreciated by the broader public and maybe even many in the scientific community at the time, but it was absolutely laying the fertile ground for future revolutions.
It really is a classic case of foundational research quietly laying groundwork that isn't immediately obvious in its full transformative scope. You don't always see the earthquake coming. From Bell Labs, LeCun went on to a long and distinguished tenure at the current Institute of Mathematical Sciences at New York University, NYU.
Right.
And of course, his current role as the chief AI scientist at Meta's fundamental AI research, or Fair Group isn't just a title. This position clearly demonstrates his immense influence on the AI direction of one of the world's largest and most forward-looking tech companies. He's not just a theorist, he's actively shaping real-world AI development.
So his career trajectory itself speaks volumes. It really highlights his unwavering status as a foundational figure in AI, a rare blend of academic rigor and industry impact. And this was officially recognized in 2018 when he shared the prestigious ACM/AM Turing Award with Geoffrey Hinton and Yoshua Bengio.
The Nobel Prize of Computing.
Exactly. That award wasn't just for a single breakthrough. It was a collective acknowledgement of their work that, as the citation profoundly puts it, turned a fringe idea into a transformative technology.
Yeah.
They resurrected neural networks from obscurity and demonstrated their immense practical utility, leading directly to the deep learning revolution we are living through right now.
Indeed. It's difficult to overstate how critical their collective insights were. If we connect this to the bigger picture, they essentially showed the world that neural networks weren't just theoretical curiosities, but powerful tools capable of solving real-world problems. This paradigm shift ignited the deep learning revolution, a revolution that LeCun had been championing for decades, really.
Speaking of those groundbreaking contributions, we absolutely have to start with convolutional neural networks, or CNNs, and their profound impact. You know, these things are everywhere now, from the facial recognition on your smartphone to sophisticated medical image analysis that helps diagnose diseases. But how did this all begin, and what exactly made his CNN so groundbreaking at the time?
It really crystallized with the Linnet 5 architecture. That was a landmark CNN that LeCun and his team meticulously developed. Its innovation lay in its elegant design, alternating layers of convolutions and subsampling.
Okay, break that down a bit. Convolutions and subsampling.
Right. Imagine your eye looking at an image. Instead of processing every single pixel individually, your brain looks for patterns, right? Features like edges, corners, or textures. A convolutional layer in a CNN does something similar. It sweeps a small filter, or kernel, over the input, detecting specific features across the entire image.
So it's like a focus spotlight looking for particular patterns, no matter where they are in the image, like finding all the vertical lines, maybe?
Precisely. And the subsampling layers then compress the information, basically reducing the spatial resolution while preserving the most important features found by the convolutions. LeCun described this beautifully. A large degree of invariance to geometric transformations of the input can be achieved with this progressive reduction of spatial resolution, compensated by a progressive increase of the richness of the representation.
Okay, let me try to unpack that. So you zoom out a bit, but you get a richer understanding of what you're seeing.
Exactly. What this means for you, the listener, is that the network learns to extract increasingly complex features, from simple edges to parts of objects like eyes or wheels, while simultaneously becoming less sensitive to where those features appear or if they're slightly rotated or scaled. It's like recognizing a 7 whether it's perfectly upright or slightly slanted, bold or thin. That robustness is key.
That makes perfect sense. So it could recognize a digit 7, whether it was slightly shifted, scaled, or even a bit rotated, which is what gives it that large degree of invariance to geometric transformations.
Mm-hmm.
How did they manage to train such a sophisticated system effectively back then? Especially given the computational limitations of the 1990s. That couldn't have been easy.
No, definitely not. They leveraged backpropagation, which was already known, but they innovated by modifying it specifically for weight sharing in CNNs. This modification was absolutely crucial. Think of it this way. Instead of having a completely different set of parameters or weights for every single part of an image.
Those would be enormous.
Huge, yeah. Weight sharing meant the same filter, the same pattern detector could be applied across different regions. This dramatically reduced the number of parameters the network needed to learn. It made the training much more efficient and allowed them to build and effectively train far larger and deeper architectures than previously possible. It was a masterstroke in making neural networks practical for real-world image processing.
And the real-world applications of this work were immediate and profoundly impactful. We're not just talking about academic papers. This wasn't confined to a lab, was it?
Not at all. His generalized transduction engine, which was incredibly compact, described as only a few hundred lines of code, was commercially deployed as a check reading system.
Wait, a few hundred lines of code for something that powerful?
That's what the description says, remarkably efficient. And it was literally reading millions of business and personal checks per day, processing a staggering volume of financial transactions. That's a tangible, massive impact from early AI research that most people probably never even knew about.
Okay, what is a generalized transduction engine, though, and what made it so efficient for a task like reading checks? That sounds quite specialized.
That's an excellent question, and it highlights a core principle of his early work. Imagine a system that takes an input like a messy handwritten number on a check and directly spits out the correct digital number without needing a separate, slow, multi-stage thinking or parsing process in between. That's essentially what his generalized transduction engine did. It was a direct, highly efficient conversion from input to output, specifically optimized for tasks like reading checks where speed and accuracy were paramount. It learned to map complex, variable inputs directly to their correct outputs. Super robust, super performant for large-scale commercial use.
What's fascinating here is how these principles, while pioneering, were also inspired by earlier concepts like Fukushima's neocognitron, a hierarchical neural network, so building on previous work.
Absolutely. Science is iterative. This blend of prior art and novel approaches laid the essential groundwork for modern computer vision. Without CNNs, the advancements we see today in image recognition, self-driving cars, medical diagnostics, and even some aspects of generative AI that process visual data simply would not have been possible. They gave machines eyes in a truly meaningful way.
Yes, it was the fundamental architectural blueprint. Okay, so that's CNNs. Now, moving beyond that, LeCun's current focus and what he sees as a crucial path forward for achieving truly intelligent systems is self-supervised learning, or SSL, and representation learning.
Right.
This isn't just an incremental improvement on existing methods, is it? It sounds like a fundamental shift in how AI learns, moving away from relying on painstakingly labeled data.
That's a huge shift. Exactly. We hear a lot about how current AI needs massive human-annotated datasets, terabytes and terabytes of labeled images or text.
So what's his vision for learning with less labeled data? He laid this out in his influential 2022 position paper, didn't he? A Path Towards Autonomous Machine Intelligence.
He did, and his core proposal for achieving autonomous intelligence combines a few key elements. First, and arguably most central, is a configurable predictive world model.
A world model. Like the AI builds its own internal simulation of reality.
Pretty much, yeah. Imagine a child learning about the world. They drop a toy, and it falls. They push a block, and it moves. They build an intuitive understanding of physics and causality through interaction, right?
Trial and error.
LeCun envisions machines doing the same. Learning and predicting future world states based on imagined actions within this internal model, not just reacting to past data, but predicting outcomes of potential futures.
So it's not just reacting to data it's seen before, but actively constructing a mental model of how the world works and then anticipating consequences based on its own actions within that simulated reality. That sounds incredibly powerful.
Exactly. It's moving from passive observation to active predictive understanding. It's a profound difference. Second, the system is driven by behavior driven through intrinsic motivation, where the AI minimizes a scalar energy or discomfort level.
Intrinsic motivation, like curiosity.
Sort of, yeah. It's a very interesting parallel to how biological systems learn. Think of how a cat learns. It explores, plays, and tries to reduce uncertainty or negative sensations. It's driven by an innate curiosity and a desire to achieve a state of comfort or predictability within its environment, rather than just being given explicit rewards like in standard reinforcement learning.
Okay.
This fosters more natural, efficient exploration and learning of common sense. And third, it leverages hierarchical joint embedding architectures trained with self-supervised learning to build these world models.
Okay, hierarchical joint embedding architecture. So let's break that down. JPA joint embedding predictive architecture is a key component of this SSL vision, right? Central to how these world models actually learn. How does that work? Especially this idea of predicting representations rather than every detail.
Right, JPA. This is where the true brilliance lies, I think. It's designed to predict representations, which they call sex and say, rather than trying to predict every single pixel or detail of the output Y. Think of it like this. Instead of trying to predict every single pixel in a future video frame, which is an impossibly complex and computationally expensive task, JPA aims to predict what's happening at a more abstract, meaningful level.
Ah, okay. So The important stuff.
Exactly.
Yeah.
It learns to create a mental blueprint of, say, a car's trajectory, its speed, its intended turn, its interaction with the environment, rather than all the distracting minutia of the pavement texture or the passing trees.
So it's about discerning what's important and intelligently filtering out the noise, almost like our brains do when we're focusing.
Yeah.
Like you don't notice the hum of the fridge after a while.
Precisely. This allows the encoders, the parts of the network that process the input, to eliminate irrelevant details. For instance, if you're looking at a video of a car approaching a fork in the road, the JIPA model would focus on critical information like the car's position, orientation, and velocity, and whether it's likely taking the left or right branch. It would intelligently ignore less relevant details like the exact texture of the sidewalk or the specific species of trees bordering the road. It focuses on the gist of the situation, the core meaning, just like you would.
That makes the process much more efficient and allows for better generalization, I imagine. But how does it handle the real-world uncertainty inherent in predictions? The world isn't perfectly predictable after all. Cars swerve, things happen.
That's where latent variables come in, and it's a crucial innovation. The real world isn't perfectly predictable. There are always elements of uncertainty. So JIPA incorporates latent variables, which are like internal hidden choices the model considers. If, for example, the car could plausibly take either the left or right branch at the fork, the latent variable z would represent that choice.
Okay.
This allows the model to generate multiple plausible predictions for different future scenarios, rather than trying to force one single, potentially incorrect outcome. This enables the model to handle multimodal dependencies through encoder invariance, meaning different inputs that lead to the same core outcome can be mapped to the same efficient representation.
So whether a car is moving fast or slow, or is viewed from slightly different angles, the system learns to extract the same essential carness and its trajectory without getting bogged down in every tiny visual variation.
Exactly that. It learns the essence.
So instead of trying to predict every pixel in a video frame or every word in a sentence, it's predicting a more abstract, meaningful representation of what's happening or what's being communicated. That sounds like a much more intelligent way to learn. Smarter, not just bigger.
Yes, and this approach is designed to enable machines to learn as efficiently as humans and animals. That's the goal, to learn representations of percepts and action plans across multiple levels of abstraction, from low-level sensory data to high-level goals. This multi-level understanding is absolutely crucial for sophisticated reasoning, robust prediction, and effective planning in complex dynamic environments. It's a significant departure from simply predicting the next token in a sequence, which is the primary mode of operation for many current large language models.
And this brings us to one of Yann LeCun's most central and, frankly, most provocative stances. His sharp critique of current large language models, or LLMs, for achieving artificial general intelligence, or AGI. He famously said, and it's a quote that continues to reverberate, that AI is dumber than a cat. This was his sentiment as of 2024, and he clearly seems to maintain it. What specifically does he mean by this? Why does he believe that LLMs, despite their impressive capabilities, will not lead to true AGI?
He uses the dumber than a cat analogy not to disparage the incredible linguistic abilities of LLMs, which are obviously impressive,
Sure, they can write amazing things.
but to highlight a fundamental missing piece: common sense. Think about what a cat can do, a house cat even. It understands basic physics, that objects fall, that one object can push another, that walls are solid. It can plan a route to jump onto a shelf or hunt prey, anticipating its movements.
Right. Intuitive physics.
Exactly. It has a basic understanding of object permanence. If a toy goes behind the couch, the cat knows it's still there. LLMs, despite their vast knowledge gleaned from text, fundamentally struggle with these seemingly simple, intuitive tasks that are second nature to a cat or, a human toddler.
So for him, it's not just about bigger models and more data.
Yep.
What's the core issue he sees with the current scaling trajectory of LLMs? Just making them bigger isn't the answer.
His assertion is clear. Autoregressive language models will not scale to AGI, and he maintains that human-level artificial intelligence is going to take a long time. A long time. He argues that relying solely on scaling and incremental improvements without integrating common sense leads to asymptotic performance limitations, meaning you hit a ceiling. LLMs are incredibly adept at pattern recognition and sequence generation from text. They can mimic human writing, engage in conversations, and even write code remarkably well, but they often operate based on statistical correlations without truly comprehending underlying causal relationships. They might be causal parrots, as some researchers describe.
Causal parrots, I like that.
Brilliantly mimicking understanding rather than genuinely causal models that understand why things happen. You can ask an LLM to plan a complex physical action, and it might generate a perfectly coherent sounding text description, but it won't be able to actually execute it in the real world because it lacks a fundamental understanding of physics or embodiment. It hasn't lived in the world.
This raises an important question. What does he mean by common sense, specifically? And why is it so essential for AI, especially if we're talking about true autonomy?
For LeCun, common sense is essential for autonomy. It's the ability for AI to adapt to new, unforeseen situations, make intuitive decisions, and operate efficiently without requiring exhaustive computational demands for every single possible scenario. He believes this fundamentally requires physical and cognitive embodiment within a well-defined domains.
Embodiment. So it needs a body, or at least a way to interact physically?
Essentially, yes. AI needs to learn through interaction with the physical world, manipulating objects, experiencing cause and effect, and building an internal model of reality, not just from vast amounts of text or static images. This contrasts sharply with the purely text-based training paradigms of many current LLMs, which operate in a disembodied, abstract space. They know the word gravity, but they don't feel it.
So it's about truly understanding the world, not just predicting the next word based on statistical patterns. He also advocates for a fundamental redesign of AI software architectures. What does that entail? Is he saying we need to throw out everything we've built so far? Like start over?
Not entirely throw out, perhaps, but certainly a radical rethinking. It means moving beyond merely optimizing existing transformer architectures, which rely heavily on self-attention and are, frankly, computationally demanding for very long sequences, especially for complex reasoning tasks. He suggests integrating insights from cognitive science and neuroscience to build AI systems that learn and reason more like biological intelligence.
Looking to nature again.
Right. His advocacy for research directions that pursue planning and more general animal-like capability is a clear signal of this. He sees this as a more promising, more efficient, and ultimately more scalable path to what some might call AGI, rather than just endlessly scaling models that lack fundamental understanding of physical reality or causality. He envisions systems that learn from observation and action in an interactive environment, actively exploring, not just passively processing static data.
That's a fascinating philosophical and architectural stance, one that stands in stark contrast to the scaling hypothesis that dominates much of the AI landscape. Now, shifting to his current work and views, especially within Meta AI, how does his outspoken perspective on AGI and LLM limitations square with Meta's actual products, like the powerful Llama series? It feels like a bit of a paradox, doesn't it?
It's an interesting and important duality, and it highlights his pragmatic approach, I think. While LeCun's primary public stance suggests AGI is distant and that LLMs won't get us there alone, his work at Meta clearly involves practical engagement with AI safety and capability for current models. For instance, Meta's Llama 3.1, released in July 2024, includes new security and safety tools such as Llama Guard 3 and Prompt Guard.
Right, the guardrails.
Exactly. This demonstrates a commitment to responsible AI development for the powerful models they're deploying today, even if his long-term research focus remains on more fundamental, architecturally different approaches to intelligence. He's working to make the current tools as good and as safe as possible, while simultaneously pushing for the next generation of AI. You have to manage the present while building the future.
So even while he's questioning the ultimate path of LLMs for AGI, he's actively contributing to making them safer and more robust in the present. That makes sense. This brings up the broader industry debate on AI safety and the choice between open sourcing powerful AI systems versus keeping them closed. Meta, of course, has a public and very vocal commitment to openly accessible AI.
Yes, and this strategic choice, articulated very clearly by Mark Zuckerberg, is framed as being good for developers, good for Meta, and good for the world. The argument is that open access accelerates innovation and fosters a more transparent, collaborative ecosystem.
Okay, but what are the risks? Some people are pretty worried about open sourcing powerful AI.
And that's a crucial point for you, the listener, to acknowledge. Open sourcing powerful AI systems does come with its own set of safety considerations. Some, particularly proponents of closed source models, liken it to the complexities of regulating powerful technologies, even weapons, arguing that widespread, uncontrolled access could lead to misuse.
Right, the dual use problem.
Precisely. Meta's position, championed by LeCun, is that the benefits of open innovation outweigh the risks, and that broader community engagement actually leads to better, safer AI in the long run because more eyes find more problems.
Interesting. Speaking of trends, let's revisit his critique of generative AI and scaling laws. He maintains this view that current AI is dumber than a cat, a claim that might seem dated to some given the rapid advancements, but still captures his core sentiment about a lack of common sense. What's the underlying argument there against relying solely on scaling?
His argument is that while scaling laws have undeniably led to impressive emergent capabilities for specific tasks like generating coherent text or stunning images, they don't inherently lead to true common sense or generalized intelligence that can adapt to novel physical situations. The cat test, if you will.
Yeah.
Moreover, the computational cost and energy demands of endlessly scaling these very large LLMs are becoming a significant and potentially unsustainable counterpoint.
The energy cost is huge, right? I've read about that.
It's enormous. Training these models is incredibly energy intensive, requiring vast data centers that consume prodigious amounts of electricity. You hear stories, maybe slightly exaggerated but indicative, of data center operators wanting to acquire nuclear power plants just to support their capacity needs. Major tech companies like Google and Microsoft each consume more power than some small countries. This raises serious questions about sustainability if uncontrolled scaling is indeed the only path forward. Can we afford it, environmentally and economically?
It seems like a lot of people in the field are starting to feel this way, even some who were big proponents of scaling initially. Didn't Ilya Sutskever, OpenAI's former chief scientist, express something similar?
He absolutely did. Sutskever, one of the key architects of scaling, noted publicly something like, "The 2010s were the age of scaling. Now we're back in the age of wonder and discovery once again. Everyone is looking for the next thing. Scaling the right thing matters more now than ever."
Scaling the right thing.
Exactly. This statement, coming from one of scaling's earliest and most prominent proponents, indicates a broader rethinking within the AI community. It aligns quite directly with LeCun's long-held views on the need for new, more efficient, and fundamentally different architectural paradigms for true intelligence, rather than just brute force computational power.
That's a powerful shift in perspective from within the industry itself. Wow. Now let's talk about Meta's Llama strategy, which is a big part of their commitment to open source AI and a significant counter-narrative to closed source models.
Yeah.
What's the significance of Llama 3.1, for instance, released summer 2024?
Meta's Llama 3.1 is indeed positioned as their most capable model to date, and a direct challenge to the closed source giants like OpenAI's GPT series or Google's Gemini. It boasts an expanded 128K context length.
Which means it can handle much longer inputs, like whole books.
Potentially, yes. Much longer documents or conversations, certainly. It also supports 8 languages, significantly broadening its utility globally. Notably, the Llama 3.1 405B model, that's 405 billion parameters, is touted as the first frontier-level open-source AI model, meaning it's designed to rival the capabilities of the best closed-source models that you can't just download and run yourself. This model is engineered to offer unmatched flexibility and control to developers, enabling them to build on its foundation without proprietary restrictions. That's the open source promise.
That's significant. How do they achieve such advancements, especially with an open source model? And what does the post-training process involve for something like Llama 3.1? It's not just about the initial massive training run, is it?
No, the post-training process for Llama 3.1 is quite sophisticated and involves several rounds of alignment on top of the initial pre-trained model. This makes it safer and more helpful. This includes supervised fine-tuning, SFT, rejection sampling, RS, and direct preference optimization, DPO.
Okay, SFT, RS, DPO. Can you simplify those a bit?
Sure. Think of supervised fine-tuning, SFT, as giving the model direct, labeled examples of what good behavior looks like teaching a student with specific practice problems and correct answers. Rejection sampling, RS, is like a quality control filter. The model generates multiple responses, and the less desirable ones are identified and rejected, helping it learn what not to do, sort of learning from mistakes. And direct preference optimization, DPO, is where the model learns by comparing 2 or more options and explicitly picking the better one, much like a human grading an essay or picking the preferred response in a chatbot evaluation. It learns preferences directly.
So it's an iterative refinement process, layering these techniques. And you mentioned they use a lot of synthetic data for this, AI teaching AI.
Exactly. The vast majority of their supervised fine-tuning examples are generated using synthetic data, meaning it's AI-generated data designed to teach the models specific behaviors or knowledge. They iterate on this process to produce higher and higher quality synthetic data across all capabilities, which allows them to efficiently scale the amount of fine-tuning data without relying solely on human-labeled examples, which can be slow and expensive to collect.
Interesting. So beyond just the technical advancements, what are the specific strategic benefits Meta sees in this open source approach? And why does it align with LeCun's vision, even though he's critical of LLMs reaching AGI?
The benefits, as Meta articulates, are multifaceted. First, it offers greater flexibility and customization for companies and developers to fine-tune the model to their specific needs, enabling highly specialized applications you might not get off the shelf. Second, it fosters rapid innovation driven by a broader global developer community. They can adapt the technology to new challenges or integrate it with other systems without waiting for vendor updates. It's like crowdsourcing
Yeah.
innovation.
Like leveraging the global brain.
Kind of, yeah. This crowdsourcing of information and collective problem solving dramatically accelerates the model's advancement and robustness. More people looking at it, trying things, fixing bugs. And third, it builds a vibrant ecosystem. Meta highlighted over 25 partners like AWS, NVIDIA, Google Cloud, and Databricks, offering services built on Llama 3.1 from day one. This reflects a strategic counterposition to solely closed-source models, emphasizing community-driven progress, transparency, and the democratizing of powerful AI tools, which aligns perfectly with LeCun's long-standing belief that innovation thrives best in an open environment.
This really brings us to the heart of some major controversies and debates in the AI world, and Yann LeCun is often right in the middle of them, sometimes stirring the pot quite deliberately, it seems. Let's start with the AGI definition debate, where his stance is particularly strong and, as you mentioned, quite provocative.
This is where it gets really interesting and, frankly, a bit heated within the AI community. The common understanding of artificial general intelligence, or AGI, typically refers to AI with human-level general cognitive abilities, the capacity to understand, learn, and apply intelligence across virtually any intellectual task a human can. That's the usual definition, more or less.
Okay, that's reasonable.
However, LeCun often redefines the term AGI in his own idiosyncratic and completely insane way, as one rather frustrated observer put it online. And then, having set his own definition, which is often much more encompassing, requiring true embodiment, common sense, and animal-like learning efficiency, things current systems lack, he dismisses the concept as used by others, and sometimes, yeah, quite aggressively stating that anyone who talks about AGI is a moron.
Wow, okay. That's quite a strong statement. So it's not that he doesn't believe in advanced intelligence eventually, but he takes issue with the current use, the perhaps misleading hype, and the very definition of AGI as others apply it today.
It seems to be a bit of both. He argues that the term AGI, as commonly used, is ill-defined and contributes to a kind of magical thinking, implying that simply scaling up current LLMs will spontaneously lead to human-like general intelligence. He believes this is a dangerous distraction from the fundamental architectural breakthroughs he thinks are necessary. His aggressive rhetoric, while definitely controversial, serves to maybe shock people into reconsidering their assumptions about AGI and the path to achieving it.
Creates friction, forces people to think.
Exactly. It creates friction, certainly, but it also forces a deeper examination of what we truly mean by intelligence in machines, beyond just task performance.
And what about the LLM scaling debate? Where does he stand there, especially given the astounding success and capabilities of models like GPT-4, Claude, or even Meta's own Llama 3.1? Many would argue that these models are indeed showing emergent intelligence simply by getting larger.
His firm belief, as we touched on, is that autoregressive LLMs are doomed to reach true AGI. He just doesn't see it happening with that architecture. He contends that simply making these models larger and feeding them ever more data won't inherently imbue them with common sense, a robust understanding of the physical world, or the ability to plan and reason effectively in dynamic environments. The core limitations remain, in his view.
What limitations specifically?
He points to their inherent struggles with complex, multi-step reasoning, counterfactual thinking, what-if scenarios, and spatial reasoning outside of what's explicitly described in their training data. For example, while they can generate text about building a house, they lack any intuitive understanding of load-bearing structures or material properties in the real world. They haven't built anything. This puts him directly at odds with researchers who advocate for continued scaling of LLMs as the primary or even sole path to advanced intelligence, seeing those emergent properties as steps towards AGI. It's a fundamental disagreement on the necessary architectural and learning paradigms required for truly advanced, adaptable AI.
Right. Architecture versus scale. And finally, the ongoing debate between open source and closed source AI. LeCun, through Meta's strategy, is a key figure here, passionately advocating for open access. What are the core arguments from both sides in this high-stakes discussion? It seems fundamental to the future of AI development.
He is a central player, absolutely.
Yeah.
Meta's approach, largely championed by LeCun and Zuckerberg, promotes open source AI as the optimal driver of innovation, transparency, and accessibility. The argument for open source is compelling. It fosters a vibrant global developer community that can rapidly iterate, customize, and broadly apply the technology to countless new problems, accelerating progress far beyond what a single company could achieve alone.
More minds, faster progress.
That's the idea. It also allows for greater scrutiny and diverse inputs to enhance safety, identify biases, and democratize access to cutting-edge tools. It's a vision of collective intelligence, building collective intelligence, spreading the power.
So a more collaborative, decentralized approach that spreads the power and maybe the responsibility more widely. Makes sense. What's the counter-argument then? Why keep models closed?
Precisely. However, the counter-argument for closed-source models, championed by companies like OpenAI or Anthropic, emphasizes greater control over the technology. They argue that this control is crucial for ensuring safety and preventing misuse, especially as models become more powerful and potentially more dangerous. They believe a single, responsible entity is better equipped to manage risks, conduct rigorous testing, and control deployment carefully.
The responsible steward argument.
You could call it that. They also point to the proprietary advantage of investing vast resources in developing cutting-edge models, allowing them to capture the market value of their innovations. This is a fundamental philosophical and practical divide in the industry, a kind of trust us we know best approach versus a power to the people collective innovation approach. LeCun's position at Meta firmly plants him on the side of open access, believing it will ultimately lead to a more robust and beneficial AI ecosystem for everyone.
So what does this all mean for Yann LeCun's enduring influence and the legacy he's building in the field of AI? How will history remember him, do you think?
His impact is truly dual-faceted, isn't it? Embodying both the foundational past and the, well, provocative future of AI. On one hand, he's undeniably a foundational figure. His early work on convolutional neural networks and his refinements to backpropagation laid the literal groundwork for how machines interpret visual data. You can't talk about computer vision without talking about him.
Right. Modern computer vision, the pervasive image recognition we see everywhere, and even components within today's most advanced generative AI models for image creation owe a tremendous, enduring debt to his pioneering efforts. He gave machines eyes.
And taught them how to truly see and understand what they were looking at.
Exactly. And on the other hand, he's this relentless, provocative visionary. He's simply not content with the status quo, is he? Constantly challenging current AI paradigms, particularly around the very definition and viable path to AGI and the limitations of large language models. He's pushing us to look far beyond just bigger models and faster processing, urging us to question fundamental assumptions.
Exactly. He's advocating for a distinct alternative path to AGI, one centered on animal-like intelligence and self-supervised learning through the development of sophisticated world models. This vision emphasizes learning from interaction, curiosity, and experience in a dynamic environment, rather than purely from vast static datasets. It offers a powerful counter-narrative to the current scaling efforts that dominate much of the public conversation around AI. It suggests a more efficient, maybe more biologically inspired route to true understanding.
It's clear that LeCun's commitment to foundational research and his outspoken critiques continue to push the boundaries of what we imagine AI can be. He's urging us, and you the listener, to look beyond immediate breakthroughs, however impressive they seem, towards truly intelligent, efficient, and fundamentally understanding systems. Systems that might learn not just from vast amounts of data, but from genuinely interacting with and comprehending the world around them, much like a child, or indeed a cat.
This raises an important question for you, the listener, to ponder long after our deep dive ends. As AI continues its rapid evolution, will the ultimate path to true intelligence be paved by ever larger models processing immense datasets, akin to building taller and taller towers of information? Or will it require a fundamental rethinking of how machines learn, drawing inspiration from the common sense, intuitive physics, and embodied learning that we see in even the simplest of animals? Yann LeCun's life's work strongly suggests it's the latter, a deep architectural transformation that will lead to the next great leap in artificial intelligence.
And that's our deep dive into the revolutionary contributions and future-forward vision of Yann LeCun. What a mind, what a journey through the past, present, and future of AI. Thank you for joining us.
Thanks for listening. If you enjoyed this episode, please like, subscribe, and share. It really helps us grow. See you next time.